All right. Thanks for coming out. This is going to be a little bit different from the normal presentations that you guys have been through. All right. So let's start off with a little bit of entertainment. Last week we had one of our guys come down from the New York office to really kind of put together a video that sums up why I think this is fun.
All right, we're here, just sitting in the car. I want you to show me if you can get far. Step on the gas. Step on the gas. Step on the brakes. Step on the brakes. Now step on the gas. Step on the gas. When I say boom, 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 step on the gas. No pole in between. Come on, let's check. Step on the gas. Step on the gas. Step on the brakes. Step on the brakes. Step on the brakes. Step on the brakes. Step on the gas. Step on the gas. I'm glad you know which way to go, but it ain't gonna stop me. Here we go. Check and turn the signal to the right. Check and turn the signal to the right. Now turn to the right. Now turn to the right.
This is a closed course.
Check and turn the signals to the left. Now turn to the left.
No animals were injured. Maybe a few insects.
Whoa, ho, ho, ho! You got an emergency, can't you see? Do you know why we stopped the car? Do I know why we stopped the car? Yes, yes, what? Do you know why we stopped the car? Do I know why we stopped the car? Yes, yes, what? I forgot to close the door. You forgot to close the door.
All right. That was Parappa the Rapper from the PlayStation. My name's Aaron Higbee. This is my email address. This is my company's blog. Who am I? I really got into this. I'm not a car guy. I'm a security guy. This is more of a hobby. And I wasn't really into cars until I got this Subaru. And what was interesting to me is how much of this car was controlled by the ECU. Everything from putting down the throttle pedal. There's no more throttle cable anymore. That is just electrical signals that turn a servo motor. The torque distribution from the front and the rear, that's also controlled by the ECU. The firing of the cylinders, the deploying of the airbags, all of that is tied up in the computer. And that what was interesting to me as far as what sort of potential do I have with this car? How can I get into that ECU? How can I interface with it and maybe make it do something cool? I'd like to thank my company, Intrepidus. This has nothing to do with what we do at all. They footed the bill to send me out here to give this presentation. So thanks, guys. So what this talk is not about. Right now, as far as what people are into when it goes to cars is fuel mileage, hybrids. This isn't the talk for you. We're about using as much fuel and as much air as possible to make these cars go fast. We're not going to be playing World of Warcraft in the car, and we're not going to be doing war driving. So what this talk is about is owning the car to make it faster. So we're going to look at tools for ECU programming. We're going to look at the roles the different sensors in your car plays as far as monitoring what's going on in your engine. We're going to briefly get into performance tuning. There's tons of information about that. We won't be able to cover everything there. We're going to talk about the role Octane plays. We're going to talk about what's a dyno, how that's an expensive tool for tuning, and how we can simulate the dyno on the road. We're going to talk about the process of analyzing logs that you get from your ECU, making changes, and then other things that you have to help build more power. Fuel, octane, ignition timing, and removing pesky emissions equipment. So, another thing that we're going to get into is some technology that was really developed in World War II, misting alcohol or methanol into the intake track at certain periods of time. So that's all computer controlled these days, and there's tons of kits and things available to help really squeeze that last bit of power out of your car. And then a few other things about RFID chips in cars, car modification laws, and emissions testing. So I have a lot to get through. I thought this presentation was going to be 70 minutes, so I'm going to be speaking very fastly. If you see URLs in this presentation, don't worry about writing them down. I captured them all here, so if this is the only URL you write down, you'll be able to follow up on all the different open source projects and other URLs that I'm going to talk about in this presentation. All right, so car hackers. really, these aren't that different. These guys like to make their cars go faster. How these guys used to do it, I guess you could consider it the older generation. A lot of kids these days have never experienced a carbureted car, but is big block American iron. You get that carburetor, a couple carburetors, advance the ignition a little bit, and increase the displacement. Wedge the biggest motor that you can in that engine compartment. And Uncle Jesse's secret weapon for getting away from Boss Hogg was the moonshine. If you'll remember, the Dukes would pour alcohol into the tank, and magically the General Lee would get more power and is able to jump. Today's car hackers, we do things a little bit differently. Laptops, software, logging into the car, different reflashing protocols. You can't have a modern car and do work on it these days without knowing something about computers. Mechanics that are trained do a lot of work on all the different diagnostic systems that are all computer controlled. All right, but some things remain the same. So Uncle Jesse's moonshine on the left and the 4.5 gallon tank that I keep my methanol in on the right. The only difference is there's one in the tank, and mine is controlled by a microprocessor that reads different sensors in from the car and will miss specific amounts of methanol or alcohol depending on different parameters that are programmed in.
What's the biggest jump you've jumped?
Maybe that high, I don't know. Okay, so the old adage in hot rodding is there's no replacement for displacement. So the bigger motor that you can get in, the more torque that you can get, the more power you can get. But what we're seeing more of a trend in is smaller displacement motors that are computer controlled, that have really extensive and detailed equipment as far as opening cam valves and things, and that's all computer controlled. So here we got a big block, 7.4 liters, and here we have a tiny engine, basically a 2.5 liters. So there is actually a replacement for displacement, and that's the turbocharger. A lot of cars these days have turbochargers. On the right we have a small turbocharger that will come with most cars. And then as you get more into this hobby, you basically start buying turbochargers the size of a Chihuahua, and then you work your way up to a turbocharger the size of a Collie. But unfortunately, you just can't buy parts these days, slap them in a car, and expect to get the most performance out of that. A lot of people think you can, and you probably see a lot of these types of cars that have every part imaginable tied to it. But really, to get the power out of the parts people are adding, you have to tell the ECU about it. If you're putting in a larger turbocharger, you're going to be creating more air, and your ECU only has so many parameters that it can use to cope with that. So that has to be reprogrammed in order to not blow up your motor. So let's look at some of the methods that people have at their disposal now for changing the way that they control these sensors. One is a complete replacement of the ECU. You rip it out, you plug in a standalone unit that you program with your laptop, you set all the parameters yourself. They're quite costly. The downside is there's no ODB2 plug, and we're going to take a look at what an ODB2 plug is later. And you are not going to pass emissions because you're not going to have any access to any check engine information. What's that? It just doesn't. Usually they're meant for off-road applications, racing applications, and they can do some things that a normal ECU can't. For instance, they can just spit out mass fuel and cause an explosion at every interval to make the turbocharged spooled all the time. That's how the rally cars always kind of sound like a jet engine because they're using an aftermarket ECU that keeps that turbo spooled. Now, before reflashing, people were doing chip tuning with actual chips. They were cracking open the ECU and soldering them on. The problem with that is, you had a bigger chance or greater chance, unless you had a steady hand, of bricking your ECU. You don't want to do that. They can be quite costly. They're slower, and the programming isn't that programmable. You set it and you forget it, and you hope it gets the power that you want. Interim way that you can deal with changing the parameters of the way your engine operates is a piggyback ECU. And I like to explain this as sort of like a packet injection tool. You have all the sensors in your car coming back, giving information to the ECU. The piggyback ECU sits in between, and then it feeds information to the real ECU. So what happens is your ECU says, I want to run 15 degrees of advanced timing. The piggyback ECU intercepts that signal and says, oh, let's run 17 degrees of advanced timing, or let's run 20 pounds of boost instead of 5 pounds of boost. What's nice about these is you can edit them quickly. They are costly. It's another piece of hardware in the mix that could potentially have problems. And when you're playing with your car, especially if it's your only source of transportation, you don't want problems. Now what we have upon us is ECU Reflashing. So after 1996, every car sold in the United States and probably the world has to have this ODB2 port. Primarily what it's used for is for technicians to log in and check out the different status of things like oxygen sensors and all the different functions in your car. But what it's also being used for is, now that cars rely more heavily on the ECU, is reflashing or firmware updates. You can typically find this ODB2 cable in the driver's side underneath the steering wheel. Sometimes you have to pull a little access port or access panel to get to it. If you read the technical service bulletins for cars, a lot of the problems that they're fixing are code related. So they have to have a method of reflashing that code. And we'll talk a little bit about the challenges of creating maps and why the people need to reflash their ECU. So the problem is these auto manufacturers that are putting out firmware updates for bug fixes, they don't share or publish how these reflashing protocols work. Those have to be reverse engineered. So there's a big business for different companies like Superchips that sell these pocket handheld tuners and other tuning software. They figure out what the reflashing protocol does. They create hardware for it. Once you reflash it, then you have to figure out which parameters you edit to build power. It's a big business. People will spend $1,000 on a custom ECU flash of their car. Most people aren't going to spend $1,000 to get their PSP reflashed. But when it comes to cars, people tend to be okay with spending more money than they would their PSP. So here's a quick overview of how it's done. Someone cracks this reflashing protocol. We don't know how it's done. They might be using oscilloscopes to figure out the reflashing protocol. They might have a buddy that works at the dealership that lets them take home or spend some time on it. But somehow these different companies figure out the reflashing protocols to start building their software. The next thing you got to do is download that code. So now that you've downloaded the code for your ECU, it's just data, it's bytes, and you don't really know what these parameters do. It's all Greek to you. Changing this could make the car go faster, or it could make the airbag deploy when you honk the horn. So it really is flying blind, and it takes quite a bit of time and engineering to figure out and map all the different parameters in the ECU. You don't want to brick your car's ECU, as I mentioned. So because ECU hacking is not easy, there's a lot of R&D that's involved, expensive equipment. The companies that are putting out these products are investing in anti-piracy. They don't want people changing this code or reflashing other cars with their tools. Some of them use hardware tokens. Some of them are using lawyers. All right, so some more on the commercial ECU reflashing. So the way it was done in the past is you'd have a company like ECUtek that put together all of the R&D engineers to figure out how this works. They would license this software to a tuner. You take your car to that tuner who reflashes your car with the parameters. The upside of that is it's a great product. You know it's been flashed on thousands of cars. You're trusting your vehicle in the hands of someone who's probably got a lot more experience than you do, and chances are it's going to be a good experience. Now the industry is moving to more do-it-yourself applications, so we're going to look at how they're allowing people to do reflashing on their own, and then we're going to look at open source projects that are giving you complete control over it. So a portable tuner is exactly that. Cooter from the Dukes of Hazzard could definitely operate one of these. There's no laptop required. You plug it in, you usually pick your power level, it downloads the ECU code, it usually maintains a backup of it. It has some sort of security to it, so you just can't start reflashing every make and model of the same car. And then it allows you to upload a new code. Usually this is done in stages. They might have something for bigger flowing exhaust. They might have one for an exhaust and intake update. So they're pretty locked into what you can do. And they always err on the margin of safety. Obviously they don't want to be handing out code that's going to blow up your car. Now we have laptop-based tuners that a lot of them, or the ones that are on the market now, at least the commercial ones, they're actually shipping USB security keys, again, to tie it so that laptop can only be used to reflash your car. But what's been interesting in the past couple of years is there's been a lot of attention to open source applications. OpenECUROMs.org is a collection of ECUs where all of these guys sit around, they're hobbyists, and they figure out this is the air fuel table, this is the ignition table, this is the boost table. And they try it on their own, and they let you know if it works or not. And if you trust these guys, you might want to try it on your car. I always go in baby steps here, try a little tweak here, see how things work, and you end up gaining a little bit more comfort with these tools. These are big projects. Another one we're going to look at is Ingenuity.org. That's a specific open source tool for editing ECU maps. And then OpenECU.org. So, what can you do with complete control over your ECU? Well, you can dump a lot of fuel and create awesome backfires that shoot out your car 5 feet. Or you can blow some holes in your piston. So, this is what a piston is supposed to look like. And this is what a piston might look like if you type 99 instead of 9. So that's something that to think about when you're yielding this much power over your car. This is what a connecting rod on the left is supposed to look like. And this is what a connecting rod looks like after a cylinder decided to fire on its own because of some poor tuning or other conditions. So these are things that I keep in my mind when I hit send or commit changes. So what we're looking at here is a dyno chart of a 2006 Corvette, big American muscle, 6-liter V8. And car manufacturers, they measure horsepower to the flywheel. You lose horsepower once it's sent through the clutch, through the drivetrain, through the differential, out to the axles, into the wheels. That's drivetrain loss. And on a rear-wheel drive car, you have about a 23% drivetrain loss. So a stock Corvette puts down roughly 320 wheel horsepower and 330 foot-pounds of torque. The magazine's rated as a 400 horsepower car. So this is what a dyno is if you haven't seen one. It's a pretty intense experience. That's me in the passenger seat sitting on the laptop. They strap your car in and they put you in a low gear and you mash the pedal and it logs all the different data. This data is what you use to figure out if the changes that you're making is making power or not. So here's my little 2.5 liter. Its stock dyno numbers were 238 wheel horsepower and 242 foot-pounds of torque. Brochure says 300 horsepower, 25% drivetrain loss because it's all-wheel drive. And this is what ECU tuning does: 400 foot-pounds of torque and 397 horsepower, plus a couple little parts to get the boost going, and we'll look at some of those later. So with the drivetrain loss, that's 500 horsepower. And I bet 500 horsepower would feel really good if I didn't live in Northern Virginia where it's completely congested. All right, so let's get into making power, how it's done. We're going to do a quick introduction here. We're going to talk about the basics of it. It's a huge topic of much internet debate. If you think security guys and security forums have egos and argue online, then you haven't been on car forums. It easily trumps the security community. So, electronic fuel injection. We're going to look at the protocols. We're going to look at the different sensors involved. We're going to talk about fuel, spark, air, boost, and getting that data. These are the important sensors that make all that work, that's supplying ECU data to the ECU to make decisions. Oxygen sensors, mass airflow sensors, absolute pressure, how much boost do we have, other things that are important, and we need to know how much, what the temperature's like. All right, so fuel. Your ECU has to cope with different grades of fuel and different qualities of fuel all over the United States or where you live. Japan, Europe, they all get different types of fuel. Even here in the United States, out here on the West Coast in California, the best octane quality they can get is 91. This is horrible. It's not good for dealing with high boost performance applications. Other parts of the United States, they can get 93 octane, and some can even get 94. So, the way this works is, or the different sensors, is based on the information that it gets from these sensors. The car figures out how much injector duty cycles, how much fuel do I need to spray into these cylinders to maintain the air-fuel ratio that's in the tables in my programming. So a perfectly mixed batch, a perfect explosion of air, or mixture of air to fuel is about 14.7 parts of air to 1 part fuel, according to the textbooks. So this is called Stoich, or Lambda for the people that aren't from the U.S. I apologize for the metric system right now. If you read any of the text, most engines make the best power between 12.2 and 12.8 to 1 air-fuel ratio. Now if I go up a couple slides, it's actually a little bit ahead. We're going to look at, here we go. This is what a fuel map will look like in your car. Once you download the code and you can interpret it, it's going to tell you at these RPM ranges, at this load, we're going to try to run 14.7 pounds or 14.7 air fuel ratio. Once we start getting boosted and getting a lot more power going into those cylinders, we're creating heat. And this is a stock fuel map for this car. And I said a perfect combustion would be 14.7 to 1. But if you look in these upper load areas, the car is deciding to run air-fuel ratios in the 10s and the 11s. And the reason why it's doing that is not for fuel economy, definitely not. It's using that extra fuel to cool the cylinder charge. It's just misting that in there to cool that cylinder charge down to ward off knock. And we'll talk about knock in a bit here. So because the auto manufacturers have to cope with so many different factors, when dealing with ECU, you might be at sea level where you have more oxygen to work with, and you might be at altitude. You might have good gas, you might have bad gas. They try to play it safe. When they program the car, they're interested in making sure that people think that their engines are reliable. They're interested in getting you the best fuel economy. They're interested in emissions control. They don't want to be just dumping hydrocarbons into the cylinder because you've boosted it to keep it cool. So because all of these factors that they have to deal with, they really do play it safe, and every car can extract a lot more power out of that engine than the way that the manufacturer has programmed it. And that's the whole backing behind these industries that offer these reflashing tools. They know this. They know how to push the envelope a little bit farther and get you more power. Another thing that we need to worry about is spark. So when the cylinders reach top dead center, it's the highest point the piston can reach. And if we ignite that mixture while the cylinder is traveling up, that's called spark advance. We're going to create more pressure and create more power. The problem with spark advance is if you go too far, you get a piston like this. And at one point, you've maxed out the efficiency. You're not going to get any more power from that. Air. So we have different sensors in our car that are measuring air. And the way that these work are pretty interesting. One is a pressure sensor to figure out how much pressure is in the intake. And one of them is a little diode that tries to keep a specific temperature. So it measures in voltage, and the air is passing over it at a good rate. And what it does is it tries to keep it heated at a constant temperature. And in order for the car to figure out how much air is coming into the engine, it's based on the amount of voltage that's necessary to keep that element at a certain temperature. So that's how your car knows how much air it's ingesting. And that's one of the ways that we can get more power, by lying to the ECU about how much air is really coming in. So another way to get more air into the system, as I talked about earlier, is with superchargers and turbochargers. These create more boosts and create, and in turn, they create more heat and more pressure. So this turbocharger here, same size motor, 2.5 cylinder, puts down 800 wheel horsepower. So this is the collie-sized turbocharger, probably almost half the size of the motor in there. But if it was that easy just to keep on buying a bigger turbocharger, everyone would do that. The problem with that is with the more boost you create, the more problems you have. Boost pressurizes the air. The ECU needs to toss in more fuel to keep those cylinders cool. You have to keep those air-fuel ratios constant. You have to dump in more, bigger fuel injectors, and it snowballs from here. The larger your turbocharger is, the more parts you have to replace, and the more ECU programming that you have to do as far as telling the ECU what size your injectors are, what size your mass airflow sensor tube is. And it's also, you have to be a lot more vigilant as far as you're creating so much heat and pressure in this motor that maintenance becomes an issue. You really have to keep on top of it. So, knock. Let's figure out keeping away this knock. So knock occurs, you might have heard it referred to as pinging, detonation, pre-ignition, when that charge lights on its own without the spark plug going off. And this will happen if there's too much pressure and too much heat created in that cylinder. It will just ignite without the cylinder going off. So if you imagine all of your pistons in your motor in this precise orchestra, turning that crankshaft, if one of these puppies just decides to go off on its own, that's when we start creating problems. It really makes the car buck. It can cause a lot of damage. What you don't know, though, is that your engine is knocking all the time. Your computer has your engine block has a little sensor on it that listens for this. It's kind of like putting your ear up to the engine block. And your ECU has different maps that are here to cope with that. So if it's experiencing knock, maybe you got a bad tank of fuel, it will switch into a high detonation map. It'll pull away some ignition to bring things safe into a safety margin, and it might add more fuel to cool those cylinders down. Okay. So, downloading and reflashing. I mentioned before that every car now after 1996 has an ODB2 interface to it. This is the type of interface that we have here. It's a USB to an ODB2. These are the different protocols that it can speak. Other manufacturers might have different protocols, but these are the main ones, and this cable will be able to interface with just about any car and get this type of data off of it. Anyone in here own a Mitsubishi? All right. That guy, Rohit, can you give this guy one of these kits? All right. So this hardware costs about $100 a pop. The guys over at tactricks.com donated some of these for me to give away. So I'll be maybe asking some questions later and throwing some of these out. But in a nutshell, what this is a USB device that allows you to interface your PC to the ECU in your car. It speaks the different protocols. Right now, these ones are focused more on the Denso ECUs. So that's Mitsubishi and Subaru. But this guy is about to release ones for all the Chrysler products, all the Mazda products, all the Nissans, the Minis, and the BMWs. BMW just released a new twin-turbo platform, a 3-liter. It's going to be in their new 1 series, and that thing is going to be a beast, especially once you start hacking on that ECU. So when you plug this in, it works in Windows, Linux, OS X. It's recognized as a serial port. It's basically got built into it a USB to serial adapter. It creates a COM port, and then it allows you to run the different reflashing software. So this is ECU Flash from openecu.org, free open source project. It just so happens that this one is geared to the Subaru and Mitsubishi guys, but that doesn't mean that people can't put in the effort to remap the ECU for other manufacturers. So these guys have, over the past year and a half, completely mapped out on their own all the different parameters in the car ECU, and especially the ones that have to deal with creating power. So the way the process works is you plug that cable in. Sometimes there's a jumper underneath your dash that you have to plug in. So when you go home and check out your car, look underneath. You're going to find that ODB2 port, and you might see something that looks like a connector that's just sitting there unplugged. And you might think, oh, this is something that I hit with my foot. I need to plug it in. Usually what that is a jumper that tells the ECU we're now in reflashing mode. And if you're curious, it's not going to hurt anything at all to plug that jumper in. put that jumper in, turn the car in, and what you'll probably notice is your check engine light flashing or some other lights flashing, letting you know I'm either okay to accept a reflash or I'm either okay to dump my code onto your laptop. This process takes about 3 or 4 minutes. So, some things to think about when reflashing your car's ECU. Make sure your laptop has a full charge. Better yet, just plug it in. You don't want to be reflashing that car and have something terrible happen. Sit still. I've read on the forums about a guy who was rocking out, pulled that plug out during the middle of the reflash hose. Had to get the car, you had to take the ECU to the dealer, spend $1,000 to get another one. So sit still, plug in, you're going to be fine. So with this cable, now that we're plugged in, not only can we download the ECU, but probably one of the most important things is getting that data. So you have to have a pretty good strategy for getting that data. The different sensors that I talked about are giving you clues on how you're doing. So we're looking at a few columns here. They might be a little hard to read in the back, but I mentioned that mass airflow sensor that tries to maintain the temperature of that to let you know how much voltage or how much air is passing. This is a good indicator for you on the road. If you just did a 4th gear pull to red line and it took 4.4 volts to maintain the temperature of that sensor, and the next time you did it, it took 4.45 volts or 4.7 volts, that means you're moving a lot more air and you're making power. That's good. The other things that we want to look at in a data log is that knock sensor. It's going to tell you when you had a detonation event. Sometimes you'll feel it. You'll feel the entire car buck. That's when you're like, oh, crap. Or sometimes it'll be completely silent and you won't know, and the only thing that you'll have to realize that you've had a detonation event is by looking at the log. When that happens, you know that you need to back off the timing, add more fuel, decrease the boost, something to cope with that. So, not everyone has a dyno or a dyno nearby, but you can create your own dyno or get that data in a different way. So what I'm going to show here is the concept of road tuning. It's basically finding a long, straight road because what you want to do is take your car from a low RPM. You have the laptop plugged in. Maybe you have someone with you to operate the computer while driving. You get ready, you press log, you smash the pedal, you take it all the way to red line, and at the higher gear you do it in, the longer it takes, the more data points that you have to work with, to tweak those air fuel maps, the ignition maps, and so on. So, let's check out this process. In the first video, we did 4th gear to red line, and that took us to about 100 miles per hour. I apologize to my cameraman. But this next one, we're going to do 5th gear pull to red line. And the gearing on this car means at the end it's going to be going roughly 140 miles an hour. Closed course. In Centerville, Virginia. Everyone familiar with the Centerville racetrack? So what I'm doing now, I'm going to pause it. If I was just to smash the pedal in 1st gear and go, I wouldn't have very much data. I'd hit red line really quick, not a good test. You might do a little bit of that in the beginning to smooth out those transitions, but what I'm doing is short shifting through 1st, 2nd, 3rd, 4th until I get into 5th. That's where I want to start logging. At this point, I have it set up so I just hit the space bar to stop and start the logging. That's when you smash it, take it all the way to red line, and you're going to get a nice long pull, just like you would on a dyno that you're strapped into. Maybe not as safe, but you're going to get the data. So, once again, that man over there was sitting with me during this. Start them quicker. Hold on tight. All right. Okay, wait. I want to show you something. It's a little hard to see, but in the distance, there goes a car. It's about this point we're thinking, okay, we need to stop. I threw these videos up on YouTube later if you want to check them out. I know, this guy must not have read the sign that this was a closed course. All right. So if you're going to be doing a lot of this road dyno activity, start in the lower gears until you figure out that you have the brakes to bring you to a complete stop, and then work your way up to the higher gears. You may want to purchase an intrusion detection system for your car. This is the Valentine 1 front and rear laser radar detector. Okay. So this project is so awesome. The guys here have put in so much time figuring out all of the different parameters in the ECU flashing. How am I doing on time? All right. This will do the data logging as well as the ROM editing that code. So besides fuel, spark, and air and boost, the things that make you go faster, what else can you do? Well, we don't need that pesky speed limiter there of 146 miles an hour. We'll just bump that up to 197 miles an hour. We don't need a rev limiter, obviously. Let's just bump that up and see what it does. And for some reason, Fuji Heavy Industries, Subaru, doesn't want the car boosting to 30 psi like I want it to. So they cut the fuel there. So you need to reflash the ECU there to allow yourself to run those big turbochargers. So because we have complete control of this ECU and we can edit it and it controls everything, it's taking input from those sensors, this was a little bit interesting to me. So this is from the Department of Environmental Quality, has been preparing to implement an ODB2 inspection procedure. Effective July 1st, 2005, the new ODB2 inspection procedure becomes the official inspection process for most 1996 and newer motor vehicles. So you're not going to actually put anything in my tailpipe anymore. You're just going to plug your computer into my computer, and if my computer says I'm good, I pass emissions? Whoa. So, up on the right, we got that catalytic converter. And this stuff here on the left is this stuff that gets in the way of making power. It cleans the air and all that too, but it creates back pressure. And if we're trying to go fast, it just gets in the way. So a lot of companies sell these test pipes, these straight-through connectors that are void of cats. And these are for off-road use only, like that closed course we were testing on. And the way that it was done as far as tricking these sensors before was microprocessors soldering these O2 simulators, these different heater simulators in order to run without a catalytic converter. I'm sorry if you're a friend of the environment. I recycle, I promise you. With ECU editing, it's a two-click effort. Rear oxygen sensor circuit high, trouble code, disable. Catalytic system below efficiency below threshold, disable. So, does this work? You go on any car forum now and you're going to see guys like this posting information. Dude, I totally passed with no cats, dumping exhaust with a cutout right in there. I couldn't believe it. So, that's something else we can do with complete control of our ECU. So, dealing with knock. Remember this? We don't want that. So there's other tricks that we can use to cope with knock. We get rid of that. One is Octane. So increasing the Octane will allow us to run a higher compression ratio. Adding boost increases that and will get us more power. The higher the Octane in the fuel, the less prone it is to detonation. That's why, back in the 70s, leaded fuel was great. It's not so good as far as for the environment or catalytic converters. You can't run leaded fuel, but it does have a higher octane, 118 points of octane for a common race fuel. That's why you just can't put race fuel in your car and expect your O2 sensors and your catalytic converters to survive. So if you start reflashing to increase this pressure to get more power, most of the time if you're looking at the product manual, it's going to tell you you have to put premium fuel in your car. If you buy a supercharged or turbocharged car these days, you also have to put premium fuel. Running the higher octane lets you get away with running more boost and ignition advance. But what if you live in the unfortunate Republic of California where you only get 91 octane? These guys have figured it out. They went back to the World War II textbooks and found a technique that fighter planes were using, which was misting water or a combination of water and alcohol at certain engine loads to keep these motors alive, especially for taking off, anything that put it under load. Another thing that you can do God bless the environmentalists. We love E85 because it's 85% methanol, only 15% gas. Now, even if your car isn't equipped to run on E85, you can still put a few gallons in with your other gasoline and effectively raise the octane above that 91 octane that you might be suffering with. But a favorite method is one that's at least is gaining a lot of traction here, is misting in methanol, alcohol, water. So these are the basics that you need in order to do that. You got to have a tank to store this stuff in. I don't recommend 50% or 100% methanol. Can you imagine getting rear-ended with a big tank of methanol and a plastic tank in the back? So what I did was I started doing my mix and then throwing a match in. And as soon as the match went out, didn't ignite, then I thought, okay, this will be a good mix for me to run. Then we have, and I wonder why my wife will not ride in the car with me ever, or be seen in my car. We got the pump here. We have a relay. That relay is connected to a microcontroller that reads the sensors from the ECU and knows exactly when to turn that misting on. So the results are pretty awesome. For relatively low buck install, you can get into some of these methanol injection kits for $300 or $400. You have here's a car on 93 octane. It could only run about 21 pounds of boost and moderate ignition before detonation started occurring. After that, the car was able to run 25 pounds of boost, 3 more degrees of ignition advance, and just based on that alone, it gained 40 wheel horsepower, remember the drivetrain loss, and 87 foot-pounds of torque. That's definitely something that you can fill. And there's a ton of vendors out there that are selling these different kits that you can put in cars to do this. Reflashing software. So you remember these things? These are the pocket handheld tuners that companies are selling. They average in cost between $400 to $1,000. And rightfully so. I mean, these companies put a lot of time and effort to figure this stuff out. It's a huge undertaking on their part to really understand how this works and to put out a safe product. But now that we have open source tools that can download that code that was supposed to only be married to that, turns out we're not the only ones in this room that are thinking and worried about that. In fact, this is one of the first posts to the Open ECU forums. This is David from ECUtek, a lawyer. ECUtek, if you are concerned that you might have infringed our copyright or other intellectual property rights, or that you might do so in the future, we would be happy to discuss ways that a reasonable and amicable solution might be found. So if you even think about doing something bad, you should discuss this. And that was kind of a blow to these guys who started this project, who really wanted to figure this out. This letter was posted to the forums, and then it was sent via private message to nearly all the forum founders. But basically, what happened is this project, OpenECU.org, told them go scratch, released it, collaborated together. This was before the hardware even existed, and was able to put out an awesome product. Anyone in here own a Subaru? All right, white hat. I'm a little biased. There's your own ECU Reflashing. So, what else can be done with these high-end cars that have ECU Reflashes? Question?
Yeah, did you ever do any research for diesels? I noticed you got tanks up there, and they're more for diesel.
Yeah, no, I mean, the question was, have I done any research for diesels? No, I don't personally own a diesel. I'd love to have one to tow my Subaru around in. But these guys make awesome power with their products. I think they're probably one of the most far advanced as far as their research goes into remapping the ECU, upping the boost. And diesels in these diesel trucks, they take kindly to this sort of hacking because they have turbochargers. Cars that are turbocharged or supercharged, you can usually get a lot more power with the ECU hacks out of them. All right, so a lot of cars these days have RFID chips in them as far as the keys go. You put the key in the ignition. Before you do it, it's got to send it to, I don't know, the ECU to figure out whether or not it's going to allow you to start this car. It's a problem. If you lose your keys, you can find out it's pretty expensive to upgrade. Lexus, for instance, is going to charge you $1,000 if you lose your keys. I don't know if they're reflashing the ECU or if they're just putting a new one in and rekeying your car, but this is how a lot of these really high-end Mercedes are stolen that have these RFID chips. What they do is they get a key pair and they have the code that matches that. Open up the car and they break the console they break the steering column just like a normal jack, I guess, and they reflash the ECU with code that matches their key, and they're able to start the car and go. Another thing that's kind of been interesting that I've been keeping my eye on is the vehicle event data that's being recorded. So for safety reasons, cars are basically recording at any given time how fast you're going, especially in the event of an airbag deployment. They want to do some research. They want to figure out, at what speed did the airbags go off? Was this a fatal accident? Which airbags went off? And that information actually has been subpoenaed to convict people on, negligent driving. So your car is supposed to only record, I think it's like 8 seconds of this data, but I mean, come on, what computer now or chip now has less than 8K or 16K? Of course these things can record a lot more data than that. Another thing that's interesting, when I was writing this presentation, it was about OnStar collecting data about collisions. And what I was reading now is that in Chicago, they're beginning to trial a program where if you participate by giving your insurance company information on your driving habits, where you go and how fast you go, that you might get a break in your rates. So wouldn't it be nice to be in control of that data as well? All right. So, some final thoughts here. I love the environment. I do what I can. I understand fuel economy is important. I understand that for a lot of people, driving point A to point B and commuting that's all they do. Their car isn't fun to them. But what I ask everyone is to remember us who actually like driving our cars. This isn't my main car. I do have a more responsible commuter. And that remember that the ECU is going to play a big role in getting these fuel economy stats that the legislation might require. So it's easy to get 40 or more miles to the gallon if the ECU doesn't let you put the pedal down all the way. It's easy to get in more fuel economy if basically the government shuts down your car from going more than 55 miles an hour. So those are just some things to think about as far as different auto enthusiasts' opinion on this. I don't drive around without catalytic converters. I tried it once. It smelled bad. I went back to cats. So that's it. Thanks for the greets. Question?